talk by a known expert, Dr. Prakasha Rao ji from ISRO. He has held a lot of positions in ISRO, in senior positions in ISRO. He had his basic qualification and then MTech in electronics instrumentation from REC Warangal in 1985. And we are very honored to have such a distinguished person in our Saturday lecture series. Welcome you, sir. So I hand over the podium to you and you can continue.
Thank you, Senthilji, for your kind introduction. So this is my third lecture at JanyuTech. Maybe now you already know before I put slide what I am going to speak about because this is first two lectures for two different things. The first one was on reliability and quality of space systems. The second one was altogether different. Okay, it was on ethics, I think. Yeah, ethics. Okay. So that incidentally, for some reason, I had to make that presentation for the first time at Anand Technologies, and subsequently having seen the presentation, Abhimanyu has requested me to repeat that in JanyuTech lecture series, so that I have done. This third one is not exactly same, but some things could be common with my first lecture, reliability anyway, but basically it is about the lessons learned. So can you open my presentation, please? So why we have to worry about lessons learned? Okay. So this is one important aspect in system engineering. We should be able to, after successful completion of each project or even unsuccessful completion, we should be able to bring all the experiences together, whatever has gone wrong at various phases. If we can collect them at one place and have a collective review within an organization, okay, with respect to what went right and what went wrong, and what is the fix that is local to the project that is there. But some of the systems can be, some of the lessons can be applicable over long term for across the whole organization. So it's better for different project teams to come together once in a while, have some kind of review and pass on the lessons learned from one project to the other. So this effort is of course no way, because in every spacecraft itself, we will have so many issues, notwithstanding the claps and all that you see in the end. But there will be so many issues which would have been faced. But this is only because in a 1 hour lecture, we cannot be covering all. But this is some representative basis. I have tried to choose some experiences in different phases of system engineering for spacecraft systems. Yeah, my next slide, please. Yeah, so I am starting with generally in my presentations, this is last but one slide. Okay. But here I am starting with that. So normally everyone knows that ISRO has come quite far, and now the successes of ISRO are applauded all over the world actually. But still, it's not just for ISRO, it is true for NASA also, it is for Roscosmos also. It is true for any space agency or for any project for that matter. Though we have come a long way, we still believe space will not forgive you if you make mistakes. So it is very important that we try to avoid mistakes. And as I have told, one of the ways to not to make mistakes is to know what mistakes we have made earlier and to strengthen our systems to see that we will not be at least repeating those mistakes. New mistakes can always be made because we are human, okay, but old mistakes at least may not be repeated. Yes, next slide please. So here you can see the gloom in the faces of all the people who have later become very senior people in ISRO. But have they, okay, at that moment having some disappointment is normal whenever there is a failure, but have they left at that, or we have learned from the failure and moved ahead? So that's what makes the system different. Yeah, next slide please. Yeah, your best teacher is your last mistake. So this is the spirit of the lessons learned presentations anywhere. So how do we learn from the mistakes that we have made, and how do we see that we will not be repeating them? Yeah, next please. Okay, here I am going to cover the lessons learned in various phases of spacecraft realization. If you take the overall system engineering cycle, right from conceptual stage to the operations stage and actual field usage. So there are various stages like configuration definition, then the design and development phase is follow, then the environmental testing of the product whichever is going to be made, then general test and evaluation, integrated tests and all that, then ground handling and operations, and actual in-orbit okay, or on field, if you want to take your own example, those operations at various phases, different experiences were there. Okay, so I have tried to pick up for each of these system engineering phases couple of examples and try to tell. It is up to you to see whether you can correlate it with your own day-to-day work, whether that thinking is exactly same Xerox like would be applicable, but it will be sounding, at least even if after the presentation, even if one or two people feel that somewhere they can improve their way of working, I feel that my presentation effort is successful. Okay, next slide please. Okay, this is with respect to the configuration stage and design stage. We have lost a couple of spacecrafts. I will not be naming them, but anyway, so due to a short in the power bus. Okay, so the power bus spacecraft typically gets supply from the solar panels will be generating the power. So that will be passed through slip rings because the panels are rotating continuously and the power electronic system is inside the cuboid of the spacecraft. So the power which is generated outside and the panels are rotating, so the power has to be transferred inside through help of slip rings, because you cannot be keeping cables. If you keep direct cables, then they will get twisted. Okay, so you will not be having that kind of you cannot keep on twisting the cables. So that's why slip rings are used for transfer of power from outside the spacecraft to inside from the whatever generated from solar. So those power, once it is processed inside, the power has to be fed to various subsystems. The voltage lines will be going. So here the currents drawn will be compared to ground systems. Of course, it is very short, small. When we tell a spacecraft is very powerful in terms of remote sensing, if I take a 1 kilowatt or 2 kilowatt spacecraft is treated as a very high power, that is equivalent to 1 hour geyser power. Okay, so that is, but that is in orbit, that is seen as a very big spacecraft, and in communication spacecrafts, of course, we have some 20 kilowatts of power, even higher with the new generation of spacecrafts. But typically, even that kind of power, when it is being handled, if there is a short between live and return, it can lead to a lot of problems. So here we found that after the failure of a particular spacecraft, a national level committee was formed in ISRO. That is a very good open and transparent system. Whenever we have some failure, sometimes depending on the magnitude of failure, the failure is reviewed by a local committee or a center level committee or ISRO level organizational committee. But when it is much more significant, like Chandrayaan, or when we lost, say, inside 2D spacecraft, so that time the impact was so high, we formed our management has formed national level committees chaired by people totally outside ISRO. For example, whatever I am telling, that committee was chaired by Professor Sonde. Okay, so that is the type of openness and transparency that is there in the system. And the committee members will be from different, say DRDO, there could be some representative academic institutions, or elsewhere. Sometimes even when we had a W2M, when we had a problem, even our foreign partners, they were also part of the investigation committees. So like that, with the help of various experts, sometimes directly in ISRO and out of field also will be formed. So at that time, during the review, it was found that one of the basic reason is there is a short. For a short to occur, there should be some kind of an insulation damage. Okay? And after the insulation damage, also live and return, both lines have to get damaged at the same spot. Otherwise, you will not be. So what can cause this kind of damage? Okay? So whether the wire is insulation, is it some brittle, or is it having some characteristics? But even if it breaks down, how they can come into directly short. So that is when we investigated, we found that the kind of insulation that we were using, Kapton, which is a common insulation is used, but that is prone for whatever reason during ground assembly and integration. If there is a damage, and if it is undetected during our own testing at the ground before launch, subsequently if it happens to come the live return, that open area, if it comes closer, there is a possibility of short arcing. Okay. So once that arc comes, normally even if an arc comes, it will be extinguished immediately, because in space you don't have any kind of medium like oxygen and all are not there. so it has to be extinguished. But the type of insulation which I have mentioned, like Kapton, in the presence of vacuum, if there is a short, this can spread. That is what was phenomena called as arc tracking. So it was found that for aircrafts also, I think this issue is there. So when there is an arc strikes, it will not extinguish at that point, but it will spread. So that is called arc tracking and damage the whole wire harness bunch. The power harness bunch will be shorted. So this point we have learned during our investigations by numerous simulations. When I say now, it looks very simple, but it took some 6 to 8 months of effort. Actually, in between, all the launches of communication spacecrafts were stopped, and there was so much pressure to launch the next spacecraft. But unless you understand the reason for the failure, we will not be moving to the next spacecraft to launch. Of course, we have to understand and set right what went wrong, and then only we can move, depending on the, of course, criticality of the mission. So finally, it was found that there is another type of insulation called Spec 55. Okay, so that particular insulation, even if there is an arc, even if there is a arc strikes due to whatever damage in the wire, it will not propagate, but damage will be locally limited, limiting the damage potential. So this type of wire was used, and the power bus itself, earlier live and return lines. Of course, there are pros and cons in any engineering decision that we make. We want to combine actually live and return as a twisted pair because we want the EMI effects to be cancelled. So live and return, when you twist them together, the radiated emission, whatever is there, EMI, so that will be cancelled. The currents will be in opposite directions and they will be cancelled. That's why we were putting together. But when your other damage is much higher of losing a spacecraft itself, then we have to weigh between the options of splitting the live lines and return lines. There are trade-offs to be made, and whatever technical issues come due to EMI have to be overcome by some other means. So all those things were done, and our configuration itself was retuned for the next generation of InSat spacecrafts. So this is one place where during configuration and design phase, if we are not aware of a particular phenomena, here in this case it is a question of arc tracking for a specific insulation wire choice, so that can lead to loss of a mission itself. So that is one thing which we have done. So subsequently is operation of live and return lines, and even the springs SADA, where the solar array drive assembly through which I told slip rings, the power is transferred. So there also again, the leaf springs, they are metallic, of course, because power has to be transferred. Again, they are live and return if they are nearby, or if they are open, then there is a possibility in vacuum, because they are handling higher voltages also, there is a possibility of arcing in some particular, otherwise all spacecraft should have been lost. It has not happened. After 10-15 spacecrafts only, we found a problem. So some particular conditions under which, if it happens, we may be having an issue of arcing. So towards that, later some insulation coating had to be developed specifically, because otherwise it has to withstand high thermal loads also. So finally there was an insulation coating developed, and it was used on the SADA springs. And separation between live and return, because obviously if you can increase the separation, then you will be able to reduce the probability of arcing. But of course, it has got its own engineering implication, because once you increase the separation, then the size of the solar array drive assembly goes up, the mass of the solar array drive. These are all the trade-offs that have to be made. So no pains, no gains. So something you have to gain, something you have to lose. Finally, it is a engineering judgment which has to be made after weighing the pros and cons of each proposal, of course. Similarly, there were other things, because there are other things. I will just stop here. And one more important thing is, I am sure you also must be facing this, accounting for high power surge. So it's very important that the transient behavior of all the subsystems, whichever is drawing from power from the main bus, okay, or from the main power source, that has to be understood. And the design has to take care of these transient surges. We found it in our first remote sensing mission, RISAT, where the radar payload draws a huge power compared to all our previous remote sensing spacecraft series. Okay, there were optical payloads there the currents required were not of that high order. But here, because of the way the configuration is there, it will draw huge surge. And because of that, our power bus was dipping actually in the beginning. Same way some wheels also, the way we operate them for control of the spacecraft, it is different in a remote sensing spacecraft. So when all of them have demanded the acceleration torque immediately, at that time when four wheels are drawing the current together, it was having an impact on the bus and bus used to trip. Okay, this particular thing is in the ground itself. Other things, whatever I have explained, are in orbit after the launch. But here on ground itself, we could find this problem. Then you have to do some such suppression. Okay, and power transient behavior of each subsystem, which we were not doing earlier. But subsequent to this particular thing, every subsystem has to do the detailed characterization for the transient behavior, and also the design has to take care of some requirements from the main power source. So these are the things, and load staggering also is another important. Wherever feasible, don't try to, all the loads should not try to draw power from at the same time from same source. So if you can stagger the loads in terms of power distribution or in terms of their coming into the mission operations one by one, okay, like that, if you do, the amount of surge that is drawn can be limited. So these are all the aspects. With respect to power system design, I have told like that. For different subsystems, there are different things. But this gives an overall feel that during configuration, we have to, and design, we have to think of aspects which may not be nominally, when try to see what is the others' experience, what is the industry practices, and a thorough evaluation has to be done before configuration and design is declared complete. And the reviewers also, whoever are designing reviewing the design, they should keep all the aspects into. And if you can catalog all your, document all your previous issues, some exercise should be done to ensure that all the previous experiences are accounted for in doing the new design. Next slide, please. Okay, this is my standard slide. I explained last time, but still I'll quickly go through. This was for our induction program. Oh mummy, please give me some vegetable soap to make me grow strong from head to my toe. C for carrot, B for beetroot, T for tomato, to make me grow strong from head to my toe. P for peas, B for beans, P for potato, to cook them all together and make me some soup. Make it yummy, make it tasty, make it delicious too. I will drink it up all to the very last drop. I was thinking how to close my lecture. That time my son was singing this in bathroom at that time. Okay, some 20-30 years back maybe. Okay, so that time I thought something interesting. So I took that time cyclostyle sheets were there. I took the sheet from him, and in the ISRO bus, I was sitting and thinking. So here, if you think, there is a customer, the child, whoever is singing the song. There is a supplier, the mummy, and there is a product, vegetable soup. It has got some functional specifications: yummy, tasty, and delicious. And here there are some components: C for carrot, B for beetroot, T for tomato too. When we make spacecrafts, we have called something called declared component list. Only those components can be used. You cannot use any component which is not figuring out in declared component list. Then there is a declared materials list. So like that, P for peas, B for beans. So, and there is a declared process here. Cook them all together. So you cannot do. You have no freedom to. Customer is specifying what is the process that you have to adapt. And it has some functional specifications: yummy, tasty, delicious. And what for all this is being done, that is most important. The mission goal: to make me grow strong from my head to my toe. So the mission goal has to keep repeating. You can see once again, it will come. Okay, to make me grow strong, to make me grow strong, like that. So finally, friends, the most important aspect is drink it up all to the very last drop. That is the reliability. We don't want our spacecraft to fail before the last drop of the fuel is over. Like I said in the previous case, where INSAT 2 that sensor have failed, then your mission is lost. So we will not allow our missions to fail because of the want of the fuel. Till the fuel is over, because of want of some other subsystem failure or some failure has happened, mission should not be lost. That is our aim. That can happen when we incorporate all the reliability practices and all the lessons learned from previous missions. Next slide, please. So if we do all that, we can have the life of the spacecraft So I started with a very sorrow slide, okay, or with a slide with gloomy faces, and I want to end it with a. So here the most important aspects is never ever get deterred by failures. Kadam kadam badhate ja. So badhate ja. So you should never get deterred by failures. Always learn from the previous failures and build the next systems devoid of those failures. Then from sad faces in that first slide to the happy faces in this last slide. This is how the transition will be. So मुसीबतों को देखकर मुस्कुराना और मृत्यु को देखकर उछलना यवन का शील है, like that saying. So I think you keep up that spirit, then all your systems also will be going. Thank you.
Sir, namaste. It was a very interesting talk. This is Sai Hemant here. I hope I'm audible.
Yeah, yes, sir. Please.
Sir, I wanted to understand. There were two major failures of SpaceX that we could understand. One was when they were flying this Facebook's satellite, which was to provide internet over Africa, and another one very recently. Could you throw some light on the technical aspect of those failures? Because you said that these are discussed usually openly within the community.
Launch vehicle failures, you are telling, sir?
Yeah, launch vehicle failures.
Yeah. Honestly, I have read about them, but I'm not very confident about answering your question to this one. But basically, I think recent failure was due to a leakage. Starship, whatever recent failure Elon Musk himself has tweeted, there was leakage in one of the stages. That is more due to the workmanship, or in the design itself there was a scope that in some particular combination they can have a leakage that resulted in the destruction. I said they will never call it destruction. They wanted they tell unplanned critical disassembly, something they will tell disassembly of this one. So he has coined a new word actually, Elon Musk, for failures, because each failure he treats it as a step for learning only. So that was mainly due to leakage, sir, because rocketry is a very tough field he is attempting missions which have of magnitude which have never have been tried earlier. So and his philosophy is again not to test and fail on the field, and learn from that. He is not worried about the cost or the schedule or anything. He says he feels that you can learn quickly by allowing it to fail and just come back from that. So his philosophy is slightly different from rest of the spacefaring nations or government philosophy. So they take some chances even before launching. They may be having some doubts in a particular thing, but they don't worry about launching it as it is. But same thing is so if you want to do, you cannot do, because one Chandrayaan 2 failure, there was so much of commotion. But if Starship does this, or if SpaceX does that, nobody will question, and everybody will appreciate only. Because his philosophy is different, his kind of investment is different, and the approach also, they are very dynamic also, private company, they have a lot of freedom. So they are not following the regular space this one, whatever we tell 10 commandments and all those things. So one of their thing is learn on the field. So that's the reason these are all experimental missions mainly. Notwithstanding that, like you told, one of the so another mission which was there, some one or two field failures also can happen. That is mainly they will be due to the workmanship related.
So the other question I had was with the wars going on, is there any effect on the overall mission scheduling or planning in general in the space sector?
No, men may come and men may go, but I go on forever like that. The programs will keep going. War and all are temporarily there could be some component supply may not be there, some small shortages may come, all those things, but the program wise there will not be. Long term planning, there will not be any impact. Short term you may face hiccups, so that's not just in space, anywhere. So, thank you, sir.